And now, when the basis functions gets more and more complicated, a critical question is how do we actually construct even the element matrix, right? If we can construct these element matrices, then constructing the big finite element matrix is basically inserting different entries into the correct locations. But then the element matrix, which usually involves things like integration over an element k, okay, the derivative of wi times the derivative of wj, right? And if in two spatial dimensions, you may have also ddx, ddy, right? You may have the product of different types of derivatives. Then the critical question is, how do I perform integrals like this? It is not always the case that you will have analytical forms that comes out. So a pretty general way of computing these integrals is a method called a Gauss Quadrature. So quadrature is is just a way to say I'm going to be approximating an integral, right? So our finite difference has been a way of approximating derivatives. Quadrature means approximating integrals. Okay, like finite difference for approximating derivatives, quadrature approximates integrals with finite set of grid points. Okay, and in particular, one way to do quadrature of a function, let's say I want to integrate from 0 to 1. The most straightforward way is actually just split the space into several grid points and add the value of the function up, right? So the value of the function here plus the function here plus the function here. That's also then divide by the interval size. That's one way of doing quadrature, although it's not going to be the most accurate way. And Gauss Quadrature is a very accurate way of integrating functions that are smooth. Okay, and it finds a lot of application in finite elements because whatever way we construct the basis functions, it is usually smooth within a single element. Right, so our head functions in the one dimension is actually linear within an element. So even if you construct a bilinear basis functions or even more complex basis functions, it is usually very smooth within a single element. And therefore, the product of different basis functions are also going to be smooth within elements. So Gauss Quadrature, being very accurate for smooth functions, is usually the most preferred way of integrating the basis functions or interactions of basis functions within a single element. By the way, don't apply Gauss Quadrature to multiple elements because the functions are usually, the basis functions are usually not that smooth across elements. Right, so in our one-dimensional case, for example, the derivatives are actually discontinuous across elements, and Gauss quadratures are not accurate for non-smooth, especially discontinuous functions. Okay, so basically apply Gauss quadrature to every element. So what is Gauss quadrature? So let's talk a little bit about that. Gauss quadrature is approximating an integral from any a to b of a function f by a summation of I goes from 1 to n of wi fxi. It's basically a weighted average of the value of the function at specific grid points. And Gauss is the one who found out how do you calculate these W's and how do you calculate the X's so that the approximation is the most accurate in the following sense. It can integrate exactly a polynomial of as high order as possible. Okay. So, for example, if I have n equal to, let's say, 1, which means I'm allowed only evaluate the function at a single point. What do you think is the most accurate scheme I can use to integrate a polynomial exactly to as high order as possible? Yes? The center multiplied by the area. Why? What polynomial does it integrate exactly? Huh? Order 1 can integrate a linear function exactly, right? So basically, I'm saying like I want to integrate between a and b, right? And for example, if I have a constant function, then it doesn't matter, right? So wherever I choose to evaluate function, I always get the same constant, as long as my w, corresponding w, is actually equal to the b minus a. I'm fine. But now, if I have a linear function, the only place I can get the integral right is actually choose the center of the function, right? And if the center of the, because the center of the function, this cancels with that. So when n is equal to 1, I know my w1 has to be b minus a, and x1 has to be half of a plus b, right? That's the Gauss Quadrature. 1-point Gauss Quadrature. Okay. Now, if it's okay. So let me. An interesting observation is that with a single point, I actually can integrate a linear function exactly, which actually has 2 degrees of freedoms. Right? The linear function has 2 degrees freedoms because I can choose the value here and here independently. Now, with 2 points, if I have n equal to 2, what polynomial do you think I can integrate exactly? Second order, a quadratic? The interesting thing is more than that. I can integrate a third order polynomial exactly. Why do you think that's the case? Yes, every time I increase a point, I gain 2 degrees of freedoms. 1 in the location of the grid point and 2 in the weight. Okay, so every time I increase n, I get 2 additional things to play with, and I can basically solve equations to figure out how do I integrate 2 additional polynomials exactly. And the only unfortunate thing is that it's a very nonlinear problem to solve, right? So if I plug in a high order polynomial, if f is a high order polynomial, this is nonlinear with respect to the grid point locations. So it's not going to be like 2n equations, 2n. I mean, it is going to be 2n equations, 2n unknowns, but these are 2n increasingly nonlinear equations. And Gauss's contribution is actually not just to list these equations. He figured out a particularly elegant way of solving these set of 2n nonlinear equations through using orthogonal polynomials.